Now next we are going to study the second important development that led to the formulation of Bohr model of atom, that is atomic spectra. Now, what do you mean by the term spectrum? Spectrum is a band of colors obtained as a result of splitting of light is called spectrum. And the study of spectra is called spectroscopy. Now, spectra is divided into two groups. One is called emission spectra and the second is called absorption spectra. So let's first discuss what is emission spectra. Emission spectra is the spectrum obtained by the emission of radiation by a substance. Now this is obtained either by passing an electric discharge through a gas at low pressure or by heating the substance to a high temperature. Now the emission spectra can be divided into two types. The first type is continuous spectrum. Now, some spectrum have continuity of colors, that is, one color merges into the other without any gap or discontinuity. For example, splitting or spectrum of white light is an example for a continuous spectrum. Okay, now the second type of emission spectrum is line spectrum or atomic spectrum. Line or atomic spectrum. Now, atomic spectrum is observed when radiations are emitted by atoms in gaseous state. They are observed as colored lines separated by dark spaces. And each line, each colored line corresponds to a particular wavelength or frequency. And the lines, the colored lines are used to identify the element. So, in line spectrum or atomic spectrum, it is observed as colored lines separated by dark spaces. You can observe it like this. Different colored lines separated by dark spaces. Okay, so this is line or atomic spectrum, and each line corresponds to a particular wavelength or frequency, and also we get to identify from the lines which element spectrum is it. So that is line or atomic spectrum. Now the second type of spectrum is absorption spectrum. Absorption spectrum. The spectrum obtained by the absorption of radiations is known as absorption spectrum, and it is observed as dark lines separated by bright spaces. Okay, whereas line spectrum was observed as bright lines separated by dark spaces, and absorption spectrum is observed as dark lines separated by bright spaces. And the dark lines, what does the dark lines indicate? It indicates that radiations of corresponding wavelength is absorbed. Now let's study in detail about the line spectrum or atomic spectrum of hydrogen atom, because the atomic spectrum of hydrogen atom is the simplest. For other elements, the atomic spectrum is complex. So we are going to study the line spectrum or atomic spectrum of hydrogen atom. Now what do you mean by line spectrum or atomic spectrum? It is an emission spectrum, that is, it is observed when radiations are emitted from atoms in gaseous state, and they are observed as colored lines separated by dark spaces. So we are going to see the line spectrum or atomic spectrum of hydrogen atom. Next is line spectrum of hydrogen atom. Now, when electric discharge is passed through hydrogen gas at very low pressure, hydrogen molecule dissociate. When I say hydrogen molecule, it is H2. Hydrogen molecule dissociates to produce excited hydrogen atoms, which emit radiations of definite wavelength and frequency. And the spectrum obtained is called emission spectrum or atomic spectrum of hydrogen. Now, in the spectrum, we can see large number of lines appearing in different regions of wavelength. So, we get large number of lines which have different wavelengths, and the lines coming on the same wavelength are grouped together in a same region. So, we have in the atomic spectrum of hydrogen different lines appearing in different regions of wavelength and are grouped together in different series. So, depending on this, we have 5 series in the line spectrum of hydrogen, and we are going to study the name of those 5 series. The 5 series are the series. The first one is Lyman series. Second is Balmer, Passion. Fourth is Brackets. And the last one is P-fun. So, these are the names of 5 series in the spectrum of hydrogen atom: Lyman, Balmer, Passion, Bracket and P-fun. Now, we have in the series N1, whose values are 1, 2, 3, 4, 5, and N2, it is equal to N1 plus 1. So, Lyman series N2 values are from 2, 3, 4, etc. Then for Balmer series 3, 4, 5, etc. For Passion 4, 5, etc. Bracket 5, 6, etc. and P-fun 6, 7, etc. So, we have N1 and N2 values for these series. Now, N1 and N2 are integers and N2 is always greater than N1. Now, let us see in which region of the spectrum they lie. So, next we have the spectral region. Now, Lyman lies in UV region, Balmer in visible, whereas Passion, Bracket and P-fun all 3 lies in IR, infrared region. So, these are the 5 series in the atomic spectrum or line spectrum of hydrogen, and the only visible series is Balmer series. Now, a scientist named Rydberg gave a relation for calculating the wavelength of these spectral lines, and he gave an expression to calculate the wavelength of spectral lines, and the expression is nu bar. We know nu bar means wave number which is equal to 1 by lambda, the reciprocal of wavelength. Nu bar is equal to RH into 1 by N1 square minus 1 by N2 square centimeter inverse. Centimeter inverse because it is nu bar. The unit of wave number is centimeter inverse. And RH is called Rydberg's constant, and its value is 109,677 centimeter inverse. And N1 and N2 are integers, and N1 and N2 is always greater than N1. And we know if we apply this formula to Balmer series, we have N1 is equal to 2 and N2 can be 3, 4, 5, etc. Okay, and RH value we know it is 109677 centimeter inverse. We can calculate the wavelength. So this is Rydberg's relation. Now next, let's draw the energy level diagram for the line spectrum of hydrogen atom. Energy level diagram. Now we have the lowest energy state, n is equal to 1. Now energy is increasing in this order. Now suppose we have here n is equal to 2, then n equal to 3, then we have n equal to 4, n equal to 5, etc. till we have n is equal to infinity. Okay. Now here we know that the atom will absorb radiation in the ground state. Ground state means the low energy state of an atom is called its ground state. So an atom will absorb energy, and you know that the electrons present in the atom will go to higher energy state. So n is equal to 1 is the lowest energy state of an atom. On absorbing some radiation, it goes to higher energy state, which is n is equal to 2, 3, 4, 5, etc. And higher energy state is called the excited state of an atom. And the excited state of an atom is unstable. So it comes back to lower energy state. Now when it comes back to lower energy state, some of them will come back to n is equal to 1, some will come back to n equal to 2, some comes to n equal to 3, like that. So the radiations that come to n equal to 1 is grouped under the series Lyman series. So we can say the radiations emitted, because this is the line spectrum of hydrogen, it is the emission spectrum. So from n equal to 2 the radiations can be emitted, then from n equal to 3 it comes to n equal to 1, from n equal to 4 it comes to n equal to 1, n equal to 5 it comes to n equal to 1. So this is the Lyman series. Now again the electrons from n equal to 2 gets excited on absorbing radiation to higher energy level, and they come back to lower energy level and they fall in n equal to 2. In that case we get our Balmer series. So from n equal to 3 it comes to n equal to 2, n equal to 4, n equal to 5. So here we have our Balmer series. So that's why we said n1 is equal to 2 for Balmer series, and n2 can be 3, 4, 5, etc. Now next we have n equal to 3 as our Paschen series, and in Paschen series the radiations are emitted from n equal to 4, n equal to 5, n equal to 6, etc. So this is the energy level diagram of the line spectrum of hydrogen. Okay, with this the line spectrum gets over. So these are the different developments, that is the dual character of light as well as atomic spectra, that led to the formulation of Bohr model of atom. Thank you.